Newton's third law, lesson 5, part 2. So on the second page of your note sheet, we're going to go over the formulas and how to use them that we will be using in our rocket science lab, our paper rocket lab. So let's go over a few we'll be using. You're familiar with these. Distance, rate, and time formula. Well, that is distance equals rate times time. You've seen that before. Acceleration. So this is going to be the acceleration of the rocket once it leaves the launcher. There's also some acceleration as it is leaving the launcher, and we'll look at that later in this note. But the acceleration once the rocket has fully left the launcher we're going to use our acceleration formula. So acceleration, as we know from earlier note sheets, is the final velocity, VF, minus the initial velocity, or starting velocity, divided by time. And we can just make a note for ourselves. VF equals final velocity, and VI equals initial or starting velocity. Newton's second law, we went over that in earlier page. That is force equals mass times acceleration. And then launch acceleration. So that is as the rocket is leaving the launcher. So let's look at our picture here of our rocket launcher. So we have our rocket launcher, and as I mentioned before, that this is like a piece of PVC pipe here, and then the paper rocket fits over that, very tightly over that PVC pocket pipe. And so this tube of the paper rocket here is hollow, it's open, and it slides right over this, right, and then it has a cone, and then air shoots into it and it leaves the launcher. Now it's starting, it's not moving at all, and then it very quickly accelerates to the top of that PVC tube. I'm going to zoom in a little bit here, and we'll have some videos in the lab that you can watch of the rocket being launched. So it's going to move from being all the way over that PVC pipe to being a little bit up here, right? And then it's going to move a little bit higher, right? I'm just using different colors, and a little bit higher until it's finally launched. Now, of course, that's happening very quickly. But what we're calculating here, the launch acceleration, is how long it takes for that PVC, that rocket paper tube, to go from being all the way over the launch tube, the PVC pipe, to being right at the top, right? So it's going to take longer for longer rockets that have longer tubes. So the launch acceleration, we're not going to go over how to derive this equation. We're just going to take it here. It's the velocity squared, and that's going to be the this initial velocity once it leaves the launcher. That velocity squared, or VI squared, divided by 2L, and L is the length of the rocket tube. Okay, so let's look at how we might use that. We'll do a few math with these equations. So the first one, a ball is thrown straight up at a speed of 20 meters per second. How much time will it take for the ball to stop going up? Okay, so let's imagine here's a ball at the ground, and it's going straight up, and then it's coming straight back down. Right? And the speed that it's that the person has thrown it is 20 meters per second. Now, what is making it slow down? Eventually it'll go up, and it'll go slower and slower and slower until it stops here, and then it'll come back down. And that's because the pull of gravity is slowing it down. And we know that the acceleration due to gravity is negative 9.8 meters per second squared. So it's going to be pulling it, making it go slower and slower. Every second that goes by, it'll be 9.8 meters per second slower until it stops right up here. And then it will slowly start to head back down, and then it will increase its speed at 9.8 meters per second every second until it hits the ground. All right, so what formula are we going to use? How long will it take for the ball to stop going up? So we're going to use our formula, acceleration equals the final velocity minus the initial velocity divided by time. And this is the time. We don't know the time. How much time? This is what we're going to solve for, this t right here. Let's see what we do know. We know the initial speed, 20 meters per second. And actually, we know the final speed too. The final speed is right up here. How long will it take for it to stop going up? The final speed is going to be 0, right? Because it's going to be stopped right at the top before it stops coming down. And then we also know the acceleration due to gravity. It's negative 9.8. So let's plug all that in. So we're going to have negative 9.8 equals the final velocity, which is 0, minus the initial velocity, which is 20 meters per second, divided by time, which we don't know. That's our unknown, right? So let's go and solve that. So we have negative 9.8 equals 0 minus 20 is negative 20 divided by t. We want to get t by itself. So we're going to multiply both sides of the equation by t like this. And that's going to cancel there. And then we get, on this side, negative 9.8t equals negative 20. Almost there. Then we're going to divide both sides by negative 9.8. 9.8. And we get t equals 2.04 seconds. So after 2.04 seconds, the ball will stop going up and it will start coming down. All right, you're going to do a very similar problem, but now it's a rocket. Launched at a speed of 30 meters per second. How much time will it take for the, oops, I said ball, I meant rocket here, for the rocket to stop going up? So you're going to use the same math that we just did here. All the same things, and you're going to solve it, and you're going to answer it in the video. Okay, let's try some more things. So this is all math we'll use in our paper rocket lab. A rocket with a mass of 5 grams is launched into the air and falls back to the ground after 6 seconds. And the length of the rocket is 35 centimeters. So launch speed, we have to calculate these 3 things. We'll do these together, and then you'll do some on your own. All right, launch speed. We just have been doing that. That's where we're going to use this acceleration equals final velocity minus initial velocity over t. We know that the acceleration is going to be due to gravity. That's what's going to make it slow down, eventually stop, and then come back to Earth. So it's going to be negative 9.8 meters per second squared. The final velocity is going to be 0, because that is when it stops going up, right? So it's going to go up and it's going to stop and then it's going to come down to Earth. So the final velocity after it has gone up as high as it's going to go, that final velocity right at the top before it comes down is 0. So we're going to use 0 minus the initial velocity. We don't know what that is. That's going to be the launch speed, VI, initial velocity. That's what we're going to solve for. And divided by, now what is our time going to be? So we have time here. We have 6 seconds. That is when it comes all the way back down to Earth, is after 6 seconds. But we want to know, we're just talking about how long it takes to get to the top, right? Because that's going to be, we're using that the velocity of 0 when it's right here. So that's just going to be half the amount of time. We're going to divide that 6 seconds in half because it goes up half the time and then the other half the time is coming down. So we're going to divide by 3. So let's solve that. Negative 9.8 equals 0 minus initial velocity is just going to be the initial velocity, vi, I think I'll just call it v right now, divided by 3. We want to get v by itself, so we're going to multiply both sides by 3. Multiply this by 3. And then we get that v, that launch speed, initial velocity equals negative 9.8 times 3. Oh, this was negative. Right, so that's negative. The negative velocity equals negative 9.8 times 3 is negative 29.4 meters per second. So then we divide both sides by negative 1, and we get that the launch speed, initial velocity, is 29.4 meters per second. Okay. Now we're going to find the launch acceleration. Now for the launch acceleration, we have to use this equation here. So launch acceleration, we could call that AL, launch acceleration, equals v squared, which is this one, this initial velocity, divided by 2 times the length. So let's fill in what we know. So v squared, so this is the launch speed, 29.4 squared. Now here's our length, 35 centimeters. Now this is important. We have to convert to meters, right? Because all of these units of newtons and acceleration and all that, that's all in meters, not centimeters. So 35 centimeters, we could do a unit conversion. We know that there's 100 centimeters in 1 meter. And when we multiply that, we get 35 divided by 100, which equals 0.35 meters. So we're going to divide that by 2 times 0.35 meters. And let's see what we get there. Get 864.36 divided by 0.7. I don't have my calculator out. Let me take a second to do that. Hold on. 864.36 divided by 0.7 equals. Okay, I got 1,234.8, and it's an acceleration, meters per second squared. Wow, that is some impressive acceleration. So those paper rockets do accelerate really fast from the time they're on the bottom of the tube to the top of the tube because there's so much air pressure. Launch force, we're going to use force equals mass times acceleration. The mass of the rocket is 5 grams. We have to convert that to kilograms. So 5 grams, or to convert it to kilograms, we're going to multiply it. We know there's 1,000 grams in 1 kilogram. So it's going to be 5 divided by 1,000, so it's 0.005 kilograms. So we got to convert to kilograms, so the force is going to equal 0.005 kilograms times this acceleration. And I'm going to do that here. I got the force equals 6.17, and then the units for force is newtons. So that's how much force the rocket has. So it is accelerating quite a bit, but its mass is very tiny because it's a paper rocket. So its force is not all that much. Okay, you are going to do in the video questions, calculate all 3 of these things using a slightly different rocket that has a mass of 6 grams, falls back to Earth after 5 seconds, and has a length of 38 centimeters. So remember, you got to convert centimeters to meters, and you have to convert grams to kilograms. And you're going to use all the same equations. Okay, that's it.